right, so we're talking about incidence Hopf algebras, and well, my goal for today is to show you two other examples. So maybe the first one will be a little bit less interesting, but it'll be important to understand the second one. The first one is going to be the incidence Hopf algebra of lattices. And this will be an excuse to teach you about this combinatorial concept that's very important. It's going to play an important role for us. So let me say that a poset L is a lattice if for every two elements A and B, there exist two elements called the join and the meet. And the notation for join is A with a little wedge B, and this one is an upside down wedge. Well, I don't know which one is right side up or which one is upside down, but this is join and this is meet. And they have the following properties. So you want to think of the join as the least upper bound and the meet as a greatest lower bound. So the join satisfies that it's greater than or equal to A and B, and if C is greater than or equal to A and B, then C is greater than or equal to the join. Okay? And dually, the meet is less than or equal to both A and B, and if you have some element of the poset which is less than or equal to A and B, then it has to be less than or equal to the meet. Okay? And so if I draw this in the poset, imagine that I have the poset over here. Okay? That's some kind of blob, and going up in the poset. Going up in this picture means going up in the poset. Then the join is going to be the least upper bound. So basically, you're going to look at the things that are greater than or equal to A in the poset, the things that are greater than or equal to B in the poset, and the claim is that there is one special one which is greater than or equal to both, and such that if some element is greater than A and is greater than B, then it has to be greater than the join. The join. And the other way around. So the meet is going to be somewhere down here. Okay? So you can think of this as a least upper bound for A and B. And you can think of this as a greatest lower bound. So that's what it means to be a lattice. You need a join and a meet. Yep?
So we ignore that we start off with a poset and simply start off with a lattice and we define the poset as it?
So a lattice is a poset that has this property. Okay. So I mean, I could have said a lattice is a poset with the property that any two elements have a join and a meet.
I'm just asking because the way I was thinking of the lattice when I learned about it was first you start with the lattice, and then you define the poset.
Oh, I see. I see. Well, I mean, I think this is the best way for our purposes to define it. So, I guess if I'm understanding your question, you're saying that a lattice could also be defined by just defining the operations of meet and join, and then using that to define the order.
Yeah, I think the way I was taught was.
So that's fine, but I think this is going to be better for us. Okay. So let's do some examples. That will show us what kinds of things are and are not lattices. Okay. So I think very often it's more useful to see a non-example. So what is something that is not a lattice? Something like this is not a lattice. Do you agree? If I call my elements A, B, and C, every two elements should have a meet and a join. But here, you cannot really, I mean, there's no upper bound for A and C, and so there's no least upper bound. Okay? There's no way of defining what the join of A and C is. Okay? So that's something that is not. And then let's see something else that is not. So I claim that this thing is also not a lattice. Can you see why? I mean, let me say one kind of consequence of this. Any two elements need to have an upper bound, right? And so you can imagine that means that the whole poset has to have an upper bound, which is a unique top element 1. Every lattice is going to have a top element 1, which is going to be the least upper bound of everything in the poset. So anything that does not have a top element is not a lattice. Anything that does not have a bottom element is not a lattice. But this one has a top element and a bottom element, and I say that it's still not a lattice. So can you see why that is? Okay. That's right. So if you wanted to define the join of D and E, what would it be? Well, you would need a least upper bound for D and E. Now, if you look at the upper bounds for D and E, they are B, C, and A. And none of those is least. Right? There's no one upper bound that is less than or equal to all the other ones. You cannot decide if this should be B or C. So this is the kind of thing that is not a lattice. And actually, there's a join that is not well defined also, right? Which is the join of B and C. For the same reason. Okay, so let's see some things that are lattices. So, well, here's an easy example. For example, the join of these two elements is this one. The meet of these two elements is this one. Let me get them names so that we can talk about them. For example, what is the join of A and B? The least upper bound of A and B is A. So A join B is A. B join C is A. B meets C is D, etc. And you can check that every two elements there have a meet and a join. And actually, I can even do this. And this is still going to be a lattice. You can check. Any two elements have a least upper bound and a greatest lower bound. So this is an example of a lattice. Or another example is this one. Okay. The join of any pair of these two elements is this one. The meet is this one, etc. This gives you an idea of what lattices more or less look like. Okay. Let's do more interesting examples. So, other examples of lattices. Maybe maybe we can start with a really boring one. Any linearly ordered set, any chain. Whether finite or infinite. If it's totally ordered, then for any two elements, the join is the top element and the meet is the bottom of the two. So that's kind of an interesting example. A more interesting one is the poset of subsets of a set. And the order is less than or equal. Containment. Okay. So if I have two elements of this poset, then elements of this poset are subsets of S, and I want to claim that any two sets have a meet and a join. So what is the meet of A and B? The union, right? So what's the smallest thing that contains A and B? Well, it's the union of A and B. And that property over there says that if some set contains A and it contains B, then it has to contain their union. That's true. And similarly, the meet is the intersection. Okay? I should tell you that it's very common when you start this to forget which is the join and which is the meet, which one points up and which one points down, and this is maybe the best way to remember. Okay? That's kind of why the notation was chosen like this, was to mirror this one. Okay? Let's see. Another example is if we take the positive integers ordered by divisibility. Okay? So we're going to say that m is less than n if m divides n. Okay? So that's a partial order. If m divides n and n divides p, then m divides p. But if you take two random integers, there's no reason to think that one is going to divide the other. And here we also have, if we take two elements of the set A and B, they're going to be integers. What is their least upper bound? So A times B is an upper bound. It's a multiple of A and it's a multiple of B. Can you think of a smaller one? The LCM. And that's precisely what LCM means, right? Least common multiple means least upper bound in this order. So this is the LCM, the least common multiple of A and B. And, hold on. See, I told you it's easy to get these mixed up. So that's the join, right? The least number that is a multiple of A and B. And what is the greatest number that divides A and B? There's precisely a name for that, the greatest common divisor, right? Okay. So there you go. So that's another example. There's really a lot of other examples. Maybe another one, subgroups of a group. Okay. You might remember if you took my class last time that I kept calling this the subgroup lattice. And well, why is this a lattice? First of all, what is the order? So we have a group, the subgroups. We're going to consider all the subgroups and order them by containment. Okay. So what is let's say that you take two subgroups, okay? Maybe I'll call them A and B. So what is the join of A and B? Maybe let me ask an easier question first. What is the meet of A and B? So the meet of A and B is the largest subgroup that is contained inside A and B. Now, if you're contained inside A and B, that means you have to be contained inside A intersection B. But then you have to remember that if you take two subgroups of a group and you intersect them, you get a subgroup. If A and B are subgroups, then their intersection is a subgroup, and therefore it has to be the greatest lower bound. Okay? But the union of two subgroups is not a subgroup. And so we cannot just take the union here. And that's why Stephen is suggesting that I need to take something bigger than that. And there's a name for this also. What's the smallest group that contains A and B? Well, the name for that is the subgroup generated by A and B. The subgroup generated by A and B. Okay. There's many other examples. But maybe this gives you an idea of what some of them look like. Okay. So those are some easy examples of lattices. And let me just mention some easy facts about lattices. So one I already mentioned, which is that every lattice has a 0 and a 1. It has a unique lowest element and a unique highest element. Okay? And again, let's think about why that is. Let me make the argument again very quickly. For example, if you didn't have a unique minimal element, that would mean that you would have several minimal elements. But then what would be the meet of two minimal elements? You couldn't have that. So that's why you have to have a 0, and dually, that's why you have to have a 1. Let's see, what else? Let me say something else first. Well, let's say this first. So these are commutative operations. That's clear from the definition, right? And they're also associative operations, which is a little bit less obvious, but it's true. If you take A join B join C, you get the same thing as if you take A join B join C. And by the way, what is that? Well, presumably it should be the least upper bound of A, B, and C, right? And it is. Okay? And so in general, you can take the join of any finite list or the meet of any finite list, and that's well defined as well. Okay? They don't. So I don't think there's a good meaning for what it means for these to commute with each other, but there's a meaning for distributing with each other. And I'm not necessarily claiming that these two are distributive operations. So maybe it's a little bit clearer if I say each of this is commutative and associative on its own. Another property is that any interval of a lattice is a lattice. So why is that? You have a lattice, right? Let's take an interval. So this is going to be the bottom of the interval and the top of the interval. Okay? And I want to claim that this is a lattice. So I want to show that any two elements in the blue subinterval have a least upper bound and a greatest lower bound. Okay? What is the least upper bound of these two things? Well, L is a lattice, and these are elements of L, and so the least these guys do have a least upper bound. The question is whether it's blue. Can I have something like this? that this is A, this is B, and the join falls outside of my sublattice, outside of my subinterval. That cannot be. And the reason is that if you look at this element C, the top of the interval, C is greater than A, greater than or equal to A, C is greater than or equal to B. And therefore, by definition, C has to be greater than or equal to the join. Okay? So the join doesn't land outside, the join has to land inside the blue subinterval. Okay? And the same argument tells me that the meet also lands inside this blue subinterval. And these are the join and the meet operation of the subinterval. Okay? So that means that lattices are closed under taking subintervals. Okay? So maybe you see where I'm headed with this and what my next statement should be, right? What should my next statement be? Are you guys being sleepy, shy? Both? Right, so I'm showing that lattices are closed under taking subintervals, which is the first of two properties I need to be hereditary. And the second property is that lattices should be closed under taking products. So a product of two lattices is a lattice. So why is that? Well, if you have two lattices, L and M, and you look at the product of L times M, then this is kind of abstract nonsense here. So if you look at two elements of L times M, they look like a pair LM and a pair L prime M prime, where L and M are lattices. So two elements of L times M look like this. So what is the meet of these guys? I think there's only one natural guess, which is meet in the first coordinate, meet in the second coordinate, where this meet takes place in the lattice L and this one takes place in the lattice M. And the join is the same thing with joins. Okay? And you can easily check that this actually is the case. Okay? So a product of two lattices is a lattice. And that means that these guys form a hereditary family. And if they're a hereditary family, that means that they give me a Hopf algebra. Okay? So there is an incidence Hopf algebra of lattices. Okay? I guess to say what an incidence Hopf algebra is, first I need to define what the equivalence is. You need to have a hereditary family, which we have, and you need an equivalence. And you could try something fancier, but I'm going to go at least with the simplest thing, which is to say that this is just going to be isomorphism. Okay? So we have an incidence Hopf algebra generated by the isomorphism classes of lattice. Okay? Any questions about that? Are we happy with this? Yep. Okay. So, well, that wasn't too hard. Now, the trouble with this is that lattices are a very large class of posets. And they're such a large class, I mean, even though lattices have additional structure, they don't have so much actual structure to make this more interesting than what we did earlier. we have these general properties of the incidence algebra of posets. And all of those general properties are going to apply here. You know what the product is, the coproduct, the antipode. But somehow there isn't enough additional structure to say anything new, interesting about this. And that's why I was saying that it's not a particularly exciting example. It's just kind of a sub-Hopf algebra of the other Hopf algebra, and it's just something good to have if you ever need it. But I'm not going to say anything very revolutionary about this Hopf algebra of lattices that I hadn't said about the Hopf algebra of posets. Okay? So this is my first of two examples today, and I told you it was less interesting than the other one. Okay?
So it doesn't tell you anything about the lattice that impose additional structure.
The thing is that lattices are too general to say anything very interesting at this point, and so what I want to do next is focus on a smaller family of lattices where this is going to become more interesting. Okay. It's always this push and pull in mathematics between how general do you want to be and how specific do you want to be. Sometimes you want to be very general, but then you can't say so many things as if you impose more structure, then maybe you can prove more theorems. And so that is what I'm going to do next. I'm going to define another Hopf algebra of posets, a different one. Okay. And I'm going to define it in a little bit of an indirect way, so it'll take you a few minutes to understand why I'm calling this an algebra of posets, because it's going to sound different. Okay. So let me focus on a particular subfamily of lattices that is very interesting, very important. A lattice L is called distributive if, well, you can guess when, right? When should I call a lattice distributive? Presumably, if the distributive law holds. And there's not too many things that the distributive law could mean, given that we only have two operations, join and meet. So there could be two meanings to this, which are different. For example, if you look at multiplication and addition being distributive, it is true that they're distributive, but only in one sense, right? Only A times B plus C is AB plus AC. But it's not true the other way around. So what should I call distributive? That you can distribute meet over join or join over meet. So should I say that this is distributive? That would be distributing the meet over the join. Or should I say the other way around? Whichever way, this should hold for all A, B, and C in my lattice. Okay. And I think if you do this for the first time, and if you're inventing this, then you think, well, I should probably just choose one, and maybe I'll have to call these, I don't know, meet distributive or something. And then I should probably know that if I had defined it the other way around, then it would be a different notion, but that would be a very similar notion. It would be dual under reversing meet and join. There is a lucky circumstance, though, which is that actually these two are equivalent conditions. And so, in fact, I'm going to impose either one of them, and that's going to imply that they're both true. So that's a nice thing about this. So So a nice fact about this is that imposing star for all A, B, and C in my lattice is equivalent to imposing the second one for all A, B, and C in my lattice. Okay? And so if you want to check that something is distributive, you can do either one or the other one, and you're going to be fine. Okay? And you should think about this a little bit, because again, like I said, this is not true for addition or multiplication. So think about what the difference is, because multiplication satisfies that A times B plus C is A times B plus A times C, but it doesn't satisfy that A plus B times C is equal to A plus B times A plus C. And so something different is happening here, and you should think about it. The difference is that we have a lattice. So maybe I should call this a fact and an exercise. Okay. So maybe before I say more properties about this, let's test this on a few things. So for example, is this true? I mean, is this lattice that I define here distributive? If you replace meet and join by intersection and union, is it true that A union B intersection C is equal to A intersection B, A union B intersection A union C? That is true, right? That's one of the things I'm sure whenever you had to take an introduction to proofs class or something like that, you had to prove that, and so this is distributive. Is this true? So okay, so this is distributive. Is this distributive? Is it true that maybe I won't say it. Is it true that if this is GCD and this is LCM, then this property holds? Does anybody know? If you don't know, then maybe this should be an exercise. Is it true that GCDs and LCMs are distributive? This is a good question for the forum. Is it true here? If the operations were union and intersection, this would be true for the same reason it was true here. But the operations are not union and intersection, and so it's also not clear if it holds here or not. So let me also send this to the forum. Okay. But it's a pretty special property, you see. Maybe I should show you something that is not distributive, so that we have something. And I didn't come prepared, but well, I know what distributive lattices look like, so I'm going to draw something that I know is not distributive, and you're going to help me find why it's not. So a non-example, something that is not distributive. I know, and you'll see later why I know, that something like this is not distributive. Distributive lattices don't look like this. So if that's true, then you must be able to find one of these distributive relations that is not true. So can you help me find it? I'm going to guess that it doesn't involve A and E. It probably involves B, C, and D, because they have more interesting meets and joins. So I don't know, let's try something. Let's try D meet B join C. D join C. So what is this? This is D meet, the join of B and C is E. And so there's D. And is that right? Are we happy so far? So the join of B and C is the least upper bound, which is E. And then the meet of D and E is the greatest lower bound, which is D. Now let's do D meet B join D meet C. D meet B, okay, I hope this works out. D meet B is B, join. D meet C is A, and the join of B and A is B. So these are different from each other. Okay, good. It's kind of improvised, but it worked out. So in particular, this means that if you ever see this subposet in your lattice, then that this is not distributive.
There were another one earlier. I think your example earlier, we had this sort of diamond-shaped thing with the point in the maximum and minimum.
That's right. Yeah. So another example that you can check is not distributive is this one, which I drew earlier. So, okay. Now let me. Okay, so we were talking about. I'll leave this up as my non-example. And let me just tell you what these things kind of look like, just so you. Let me just draw a typical distributive lattice for you, and then you can maybe get a bit of a feel for how these things look like, how these things look. Something like that. So this is an example of a distributive lattice, and whenever you see something that looks like this, that has a lot of little cubes, then you should kind of think, okay, maybe what I'm seeing is a distributive lattice. In fact, I have a paper that started because one time I went to a talk and I saw a picture like this, and I said distributive lattice, and then we had to prove it, and then it became a paper. Okay, so whenever you see something like this, think distributive lattice, and if it's not, then ask me, and I can tell you about other things that kind of look like this. It turns out in my paper that it was not distributive, but it was something kind of distributive. Okay. So there's things that are put together from cubes in some way. There's a lot of cubes in there, and that's why I know that these things are not distributive, because they don't look so cube-like. We'll see more precisely what I mean by this. Okay, okay, so some more easy facts about this. So this was the first fact, that you just have to check one of these properties and you have the other one. Again, you might be able to guess what my next facts are going to be. Any interval of a distributive lattice is distributive. And this is just for free, because if you take a lattice and you take a subinterval, we just showed that it's a sublattice, and the operations of the sublattice are the same as the operations of the big lattice. So if the big lattice was distributive, then the small lattice ends up being distributive also. Okay? And the product of two distributive lattices is distributive. And again, this follows for free, given that I already wrote down what the operations are. I mean, I already wrote down the operations of meet and join in the product, and then it comes for free, that if the two individual lattices are distributive, then when you write down the distributive law for the product, it holds. Okay? And therefore, there is an incidence, and there is an incidence Hopf algebra which maybe I will call, what did I call it here? H of j. You'll see why I call it j. There's an incidence Hopf algebra H of j of distributive lattices. Okay. And again, you might think, okay, well, you know, that wasn't too hard. And again, it might be equally uninteresting as that one. This is clearly a sub-Hopf algebra of that one. But what I want to convince you of is that actually, because distributive lattices have such a rigid structure, it's pretty hard to be distributive. That rigid structure is going to make this object more interesting. Even though it's smaller, even though it's a sub-object, it's going to have other interesting things we can say about it that we cannot say about those. Okay. So that's what's next. Any questions about this so far? Okay. So why is it that I say that distributive lattices have so much structure? Why are they so nice? I'll tell you. Let me give you a recipe for constructing lots of distributive lattices. Lots of distributive lattices. Let me start with a poset, P. Okay. So I'm going to start with a poset. I'm going to try to always keep it blue. Let P be a, let's say everything is finite. And I meant to say finite everywhere. Hopf algebra of finite lattices, finite distributive lattices, etc. Okay. Let me define J of P to be the family of downsets of P. And let's remind ourselves what that was about. So what are downsets? So I have my poset P here. And by the way, maybe now you will notice that whenever I draw posets, I draw them like this. And you see then that my bias in combinatorics, most of the posets we study either are lattices or at least have a bottom and a top element. And that's why I keep drawing them like that. But posets don't have to look like this, but I keep doing that. Okay. So what's a downset? A downset is kind of, you look at this Hasse diagram, and you kind of look at some boundary between the things below and the things above. The downset are the things below. Okay. So it's some set that looks like this. Okay. Let's call it D. Okay. But remember that downsets are also called order ideals. So if you ever see that word, it means the same thing. So what is the property that downsets need to satisfy? D is a downset if whenever you have P less than or equal to Q in the poset. And if Q is in the downset, then P has to be in the downset. Okay, so if Q is in here and P is below it, then P has to be in here as well. Okay. Those are the downsets. I consider them all possible downsets of P. And let me order them by containment. So I put a partial order on J of P. Okay. Then this thing, J of P, is a distributive lattice. This is actually pretty easy to see because I need, first of all, why is it a lattice? So let's take two downsets, D and E downsets. So what is their meet going to be? The greatest downset contained in D and in E. If you're a subset of D and a subset of E, then you're a subset of the intersection. But it just so happens that if you take a downset D and a downset E and you intersect them, you get a downset. It's very easy to check. Right? You can see it from the picture, right? If you take some like red boundary and things below it and some blue boundary and the things below it, then the purple things that are below the red and the blue are also close under going down. What is the union? Sorry, what is the, okay, it's Jeopardy. The answer is the union. What is the question? The joint is the union because of the same thing. If you take the union of two downsets, you're going to get a downset. So this makes this a lattice. And why is it lattice distributive? Because the operations are union and intersection. And union and intersection satisfy the distributive law. Okay? So there you go. That's a distributive lattice. Let me do an example of this. But before I do the example, trying to manage my board here. Let's do an example. So I said my poset P was going to be blue. So this is any poset, any finite poset. And okay. And now let's draw J of P. So the smallest downset is the empty set. What downsets of one element do I have? 1 and 2, right? So these are the only downsets of one element. What are the downsets of two elements? Is 1 and 3 a downset? So 1, 3 is not a downset because if you contain 3, you must contain 2. 5, 2 is a downset. Any other ones? Downsets of two elements? 1, 3, 2 is a downset, but it has 3 elements. Can you think of another one of 2 elements? There is one more. 1 and 2. Right? One and 2. Okay. Now, if I have 1 and 2, what can I add next? I can add 3. That's a downset. I can add 4. That's a downset. I can add 5. That's a downset. Okay. So, for example, I have the downset 1, 2, 5. Oh, sorry, this was 2, 5, right? If 5 is in downset, 2 needs to be in there also. So this was 2, 5. Okay, but I said I can also add 1, 2. I can also add 4 or 3. Is there anything else that I can add to 2, 5? A single element. I can add 1, but I cannot add either of these guys. So that's it. Okay. 1, 2, 3. What can I add? I can add either 4 or 5. So if I add 4, I get 1, 2, 3, 4. If I add 5, I get 1, 2, 3, 5. And you start seeing where all these little cubes come from, huh? And that's all I can add. If I take 1, 2, 4, I can add either 3 or 5. So if I add 3, I get this one. If I add 5, I get this one. 1 to 5, I can add 3 or I can add 4. That's it. And then these are the ones of 4 elements, and finally the only one of 5 elements is this one. Okay. And so this is my distributive lattice coming from P. Okay. This is fun. You should do it. You should draw a picture of a poset and draw this guy. Okay, so the very nice fact is the following, and it has one of these. This one, not necessarily. This one, yes. It is true that distributive lattices are always graded. It's not obvious, but you can prove it. That would be another good exercise to put here. They're graded by what? What's the grading? It's just size, right? 0 elements, 1 element, 2 elements, 3 elements, 4 elements, 5 elements. So this is precisely what's called the fundamental theorem of finite distributive lattices. Fundamental theorem whenever you have something with such a big name, hopefully it means that we understand the objects. It means that if somebody calls it the fundamental theorem, it should mean that nobody's ever going to prove a better theorem, that this is the fundamental one. Okay? Fundamental theorem of finite distributive lattices is that we understand them all. Every single distributive lattice is one of these guys. For any finite distributive lattice L, there is a unique unique up to relabeling, up to isomorphism. Poset P such that L is isomorphic to J of P. Okay. And so maybe a more precise heading for this board is all finite distributive lattices. Okay? They all come from this construction. This is a very beautiful theorem. This is due to Birkhoff in 1947. Okay. So let me say, I'm going to give you a sketch of the proof just to give you an idea of why this theorem is true. But if you want to see a full proof, then you can probably pick up any book that treats posets thoroughly, and they should have a proof of this. The one place where I know this is written very nicely and succinctly is in Stanley's Enumerative Combinatoric Volume 1. But any book on posets should have this. Okay, but let me give you a sketch of the proof. Let's see. Maybe let's prove a lemma. And for this, I'll give you a fairly complete proof. Maybe I'll keep this example because it'll be useful. Lemma. Well, maybe a definition first. So, say an element of a lattice is joint irreducible if it is not equal to a join of two things that are not it. A, B not equal to P. Equivalently, P covers exactly one element in the poset. Okay. So let's look at what that means here. For example, 1, 2, 3 is an example of such a thing. It is not the join of smaller things. Because how could it be? There's only one thing below it. Okay. So, and for example, 1, 2, 4, 5 is not joint irreducible because it has two things below it, and so the join of those two things is it. And so it's an easy exercise to show that these two conditions are equivalent. but maybe it's easier to check the second one. So which elements here have exactly one element below them? I mean, directly below them. 1, 2, 2, 5. Anything else? One, 2, 4. And that's it. Okay. So here's a lemma. Lemma. The poset of joint irreducibles of J of P is isomorphic to P. In other words, I took this P and I constructed J of P. But what I'm claiming is that just looking at J of P, you can recover P. All you do is you look at the joint irreducible elements and you see how they compare to each other. You see there's 5 irreducible elements. And how do they compare to each other? This one is, these two are less than these two. And this one is less than this one, just like it is here. Okay. Why is it true? What's the bijection from here to here? You see, these 5 elements have the property that this one has 1, this one has 2, this one has 3, this one has 4, this one has 5. Okay? And if you look at each one of these things, each one of the elements of P, and you look at what is below them, you get the corresponding thing here. So what is below 3? 3, 1, and 2. That's this guy. What is below 4? 4, 1, and 2. What is below 5? 5 and 2. What is below 1? 1. What is below 2? 2. Yep.
Since our example poset is only 2 levels, do we mean only the things that are directly below, or do we mean the
I mean, if you take any element of P and you look at the downset generated by it, all the things that are less than or equal to it, that's going to be here. And I claim it's joint irreducible, and those are all the joint irreducible things. This will be my sketch of the proof. That's the bijection between P and the joint irreducibles here. So the bijection, the isomorphism, is that to each element of P, I associate what I might call P sub less than or equal to little p. These are the elements of P which are less than or equal to little p, which is a joint irreducible in J of P. Okay? That's the bijection. And so that shows that if you start with a poset P and you build J of P, then that tells you how to recover P.
I'm sorry, you're asserting
So that's what I'm, right, so that's why this is a sketch and not a proof. I'm claiming that this set P sub less than or equal to P is a joint irreducible, and in fact they're the only ones. So what I'm claiming is that this map from little p to P less than or equal to P is a poset isomorphism between the poset P and the poset of joint irreducibles of J of P. It means it's a bijection, and it preserves the order. So that's the first thing, and then for the second ingredient, well, so let me now give a sketch of the proof of fundamental theorem of finite distributive lattices, take L distributive, okay, and I drew one here. What is your P? Well, it should just be taking the joint irreducibles. You can do that for any distributive lattice. So take a distributive lattice like this one. Look at the joint irreducibles. This one, this one, this one, this one, and this one, and this one. Yeah. Give them names. I don't know. 1, 2, 3, 4, 5, 6, and see what poset they form. Okay. So 1 and 2 are minimal in this poset. Then 3 is bigger than 1, but not bigger than 2. 4 is bigger than 1 and 2. 5 is bigger than 1 and 2. And 6 is bigger than 4 and 3, but not 5. Right? So, and so, given L, you build P, and by the previous lemma, J of, well, so the claim is that this is the P that works. So J of P is precisely this thing. P be the set of joint irreducibles. You check that there's an isomorphism from L to J of P, and in the notes I wrote down exactly what the isomorphism is. The uniqueness comes from the lemma, because if you had two different posets such that L was J of P and it was also J of Q, then the poset of joint irreducibles would have to be P, and it would also have to be Q. So uniqueness is actually straightforward from the lemma. So uniqueness comes from the lemma. Okay. Again, I think this is all clearer from. I think the examples are clearer than anything I write down. I think now you know, if I give you a poset, you know how to build J of P, and if I give you a lattice, you know how to build the poset. And what you think is true is true. Okay. So what is the advantage of this? Let's think about the incidence algebra again. So the basis elements of my incidence algebra of distributive lattices, they are isomorphism classes of distributive lattices. Okay, but these things are in bijection with isomorphism classes of posets. Right? The bijection being take P and send it to J of P. Okay. So this is P, this is L equals J of P. Okay. What is the product? Well, if you take two distributive lattices, then the product in the incidence algebra is the direct product. Okay? But what is this at the level of posets? L1 corresponds to a poset P1. L2 corresponds to a poset P2. What is the poset of L1 times L2? I need to know what the joint irreducibles of this poset are. What do you think it is if I ask you to guess? So it turns out this is J of P1, this joint union P2. So this is a lemma. If L1 is J of P1 and L2 is J of P2, then L1 times L2 is J of the disjoint union. You put the poset here, P1 and the poset P2, and they don't interact with each other. Okay. What is the coproduct? Delta of L is the sum over my elements in L of 0x tensor x1. Okay. Let's transfer that to poset language. So if L corresponds to the poset P, then, so here you're thinking that L is J of P. What are the elements of L? The elements of L are downsets of P. So I'm summing over D, a downset of P. Okay? And I claim that what you get here is D tensor P minus D. Why is that? Because let's draw the two pictures side by side. So here's P, and here's L, which is a lot bigger. These are the order ideals of this. The coproduct is going to an element here, and then going from here to here, and from here to here. Okay? An element here is a downset here. Right? Okay? So the interval from 0 to x is isomorphic to J of D. And again, it's very easy to check that the interval from x to 1 is isomorphic to J of P minus D. So in your lattice, jumping to the middle and then to the top corresponds to, in your poset, cutting it in half and putting the bottom half on one side and the top half on the other side. Okay? And so this means that this incidence Hopf algebra of distributive lattices is really more easily understood in terms of the posets. It's a Hopf algebra generated by posets modulo isomorphism, where the product of two posets is just putting one next to each other, and the coproduct of a poset is cutting it in half in every possible way, putting the bottom half here and the top half here. Okay. And this gives me a new Hopf algebra structure on posets, different from the one that we saw earlier. For instance, Schmidt gave us a formula for the antipode of any incidence Hopf algebra, and that means that we have a formula for this particular Hopf algebra of posets, and I wrote that down in the notes so you can see it. But then here you start seeing how the general theory is allowing you to construct objects that maybe you didn't know existed. And this is a very concrete, very combinatorial Hopf algebra that comes out of the theory in a very natural way. Do you guys have any questions about this construction? Yeah, I think I won't try to rush and say anything else. So maybe this is a good place to stop. Maybe I'll just reiterate that that Tuesday's lecture by Jeremy Martin is actually recorded, so Seth was kind enough to record it, and I'm going to send you guys a link so that you can watch it. It's a very nice lecture, extremely relevant to the course. He presents this in a way slightly different from how I presented it, and so maybe it's a useful way to look at it. And actually, by those of you that were there, you should look a little bit familiar, because this was exactly, I mean, this is like the Hopf algebra of graphs, right? Product of two graphs was putting them next to each other. The coproduct was something else. Okay. Oh, and it's spring break, so you guys have a wonderful spring break, and see you guys in a couple of weeks. So you know the homework is due the Tuesday you return, which I made sure to give you enough non-spring break time for that to be fair. So if you're on top of it, then maybe you'll be done before spring break. That's good. But it's also, I mean, it is a break. But if you have time to think about possible projects, I think it's a good thing to begin thinking about. And over spring break, I'm going to prepare a list of more concrete suggestions of projects that you guys might think about, including some open questions and topics and things like this. Okay? So, you guys have a great break.
To my two homework, because I never got anything. I never heard back from the grader or anything. Those two, and it's like everybody really got it. I mean, both of them graded.
Yeah. Let me remind the grader.
At least like